Okay, so suppose K is a subfield of C. We're going to introduce something called the formal derivative, and then we're going to use that to prove that we're going to use it to prove to start proving that every irreducible polynomial over a subfield of C is separable. So suppose K subset of C is a subfield, and suppose we took some polynomial with coefficients in K, so some random one. Then the formal derivative, why is it called the formal derivative and not the actual derivative? It's because in algebra we don't have access to limits. And so it's not like the regular calculus derivative. It's just formal. It's a formal operation. There's not any limit calculus that's going on in the background. I mean, there technically is, but you can define the formal derivative in situations where you don't calculus wouldn't make sense. So you can define it over finite fields, for example, or positive characteristic fields. So anyways, that's why it's called the formal derivative. But anyways, what is it? Well, what do you think it is? It's take the derivative. So the constant goes away. A1's the new constant. There's this A2 T2 squared here, right? We bring down the 2 all the way up to bring down the n, NaN to the n minus 1. And that's what it is. So this is not new. At least it shouldn't be new. You're going to show in your homework, you will show that if you just abstractly define the derivative of a polynomial like this, that the derivative of f plus g is the derivative of f plus the derivative of g, and so linearity. And you're going to show the Leibniz rule holds, or the product rule is sometimes what it's called. So the derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. And let me just give you a hint for this right now. Let's call this L for linearity. Use L to prove it by only considering monomials. Let me not use n. AI t to the I. Basically, the linearity condition is going to tell you that if you have a polynomial, you can break it. You can just take the derivative of each of the monomials involved and then add those together. And this is also well behaved under breaking up. This formula is well behaved under addition as well. So if f was a sum, then the formula would break down as a sum. So basically what that means is, if you think through that, you really only have to prove it. So then you just need to check that when you take d of t to the I times t to the j, so that is, you only have to prove it in a special situation where f is t to the I and g is t to the j. This is just easy to check that formula. Okay. So linearity is helpful for proving the Leibniz rule. All right, cool. Oh yeah, and then one more thing that will be helpful with linearity is that's not fully linearity. It's more like, let me write that differently. F plus lambda g is d of f plus lambda d of g, where of course f and g are polynomials, and lambda is in the base field. And again, this makes sense over any field. There's nothing special about subfields of C, and that's why it's called the formal derivative. All right, cool. So in the next video, we're going to use it to prove some stuff.